My contribution to the book is an overview of the philosophical issues concerning quantum mechanics, and there's just no way I could possibly do that right now. So what I'm going to do is just think about almost 100 years of discussions of the foundations of quantum mechanics and why we're having these discussions at all. Okay. The quantum mechanics, the seminal paper is Einstein's first paper on quantum mechanics was 1925. By 1927, we pretty much have the undergraduate textbook theory that we're all familiar with. So we're coming up on the centenary. Almost 100 years of quantum theory. And as Frank's contribution to the book, the title says, we still have no consensus. Consensus about what? Well, I think the central question is, well, what, if anything, is the empirical success of quantum mechanics telling us about the physical world? And the reason I put this, if anything, is that some people have taken the lesson of quantum mechanics is that we shouldn't be talking about what's going on in the physical world at all, but only trying to relate outcomes of experiments. It's 100 years of this. Some people have called this a scandal. Some people have said this is embarrassing. Should we be embarrassed that we're still having meetings like this? Should we be hiding in a basement, Why are we still talking about this? Main message of this is relax, it's fine. I don't think there's any problem whatsoever. I don't actually think we're in a healthy situation. And because even though we haven't gotten to consensus, if we look back over what's happened in these discussions, we've got clearer about what our options are. And one of the ways to do that is to put forward concrete proposals about what the world might be doing. And the other way to get clear about our options is these limitative results, about things that you might try something, but that doesn't work. Like Bell's theorem is the classic limitative result. The sort of theory that Einstein was looking for cannot exist. So I think we're actually okay. And I think the picture that people have in their mind when they say this is a scandal and embarrassing is that prior to the quantum revolution, we lived in this beautiful pastoral Arcadian world where everything was in harmony and people understood what the world, or thought they understood what the world was like, and there was consensus about what the world was made of, what it was like at the fundamental level, and what the legitimate questions of science are. I think I used to think that. I used to think that before I had the slightest clue of what 19th century physics was actually like. People talk about the worldview of classical physics, and in the philosophical literature there's this phrase that comes up, the ontology of classical physics. Well, what is the ontology of classical physics? Well, I think among people who use that phrase, they think, okay, it's point particles moving around under central forces. Okay. And yes, that is what some people propose, notably Helmholtz. But remember, classical physics is not just the physics of point particles. Continuum mechanics has always been a part of classical physics. The book 2 of Newton's Principia is on fluid mechanics. And mechanics of rigid bodies. So the world could be made up of little bits. It could be made up of a fluid. It could be made of all things. These sorts of things were seriously suggested. And the reason is that, if I say, okay, the world is made up of little point particles moving around, that poses serious problems. What the heck is going on in a chemical reaction? Why is matter stable? Why are there only certain kinds of elements that combine with each other in certain ways? One intriguing possibility that drew some attention for a while, and Professor Krog was actually, who's here? I don't see him. There, yeah. Was one of the people who drew the attention of the community to this, is molecular vortices. So Helmholtz proved that if you have a perfect fluid, incompressible without friction, you start a little vortex going, it's permanent. Those can loop around each other. They repel each other at a short distance so they can't cross. And so, hey, maybe atoms are actually made out of a continuous fluid. and they can knot with each other in certain ways, and wouldn't be great if we could understand the structure of matter, why there's a limited number of chemical elements. Maybe those are the different kinds of knots there can be. Maybe we can explain why things combine in such ways. It drew a lot of attention from a lot of very prominent physicists, Kelvin notably, and then it sort of fizzled out because they didn't get the sort of theory that they want. But I think it was, and people looking back at this might say, okay, that was silly, that was a mistake to do it in the first place, and I think that's wrong. Well, we got clear, it was an attractive idea, and we got clearer about what our options were. People forget that, because we project consensus back, the idea that chemists were using atoms to do stoichiometry, doing calculations, but there was no consensus about whether these were only a useful bookkeeping tool, or whether they were physically real, well into the first decade of the 20th century. And one thing that happened in the 19th century, there's proliferating theories about what's going on at the fundamental level. People are inventing various ethers and other unobservable things. One view was that shouldn't be doing that. Science shouldn't be trying to peek behind the veil. Should be only trying to relate observable phenomena. Boltzmann in particular had controversies with people who thought that no, you shouldn't be doing this molecular theory. I think it's fair to say that the people who were pursuing the kinetic theory of gases, people who were pursuing molecular theory, it proved fruitful. And I want to say also that the attempt to, in the 19th century, there was no successful account of what was going on, say, why matter is stable, what happens in a chemical reaction. But I also think that avenues pursued unsuccessfully, including some that are mostly forgotten today, gave us a clear picture of what the viable options are. Now, I find this interesting because what it means is we don't need a comprehensive or coherent count of goings on at the fundamental level in order to do physics. And of course, everyone in this room is familiar with that. We know how to use quantum mechanics very well. We can do, it's a spectacular tool for technological innovation, even though there's no consensus about what it might be telling us about what the world is like. Possible to do good science without ignoring fundamental issues. Sometimes physicists give talk. I'm a philosopher. Sometimes physicists give the talk saying physicists need philosophy, and I think, well, that's kind of flattering because I'm a philosopher, but it depends on what kind of physics you're doing. You might very well get along fine without asking questions about the fundamental nature of reality. Right. Then is the moral that we shouldn't be asking those? No, I think prohibition of investigation into these fundamental issues would be a major mistake, because thinking about these things has proved fruitful. So if we think about everything we've learned about an entanglement and how to handle it, a lot of that discussion of entanglement was inspired by the EPR paper, and then Schrödinger wrote his papers on entanglement in response to EPR, and then Bell's paper, as Professor Aspect reminded us, was called On the Einstein-Podolsky-Rosen Paradox, because Bell was thinking about those sorts of things. Okay. So I think, again, the central question of foundation of quantum mechanics is, what, if anything, does the empirical success of quantum mechanics tell us about the physical world? Can we give it a coherent account of goings on in the world, and should we try? Various attitudes towards the question is, well, I think for a lot of this history in the past 100 years, a lot of physicists would probably told you, oh, they've been answered. Bohr figured this all out. In one of their paper from the early 60s, Bell and Nauenberg have a footnote where they say that they think that the attitude of most physicists is that all of these questions have been answered, and if they only had 20 minutes sometime, they'd understand what that answer is. Or, sometimes people will proclaim them illegitimate or unscientific, and I think most of the people in this room would think they are indeed worth pursuing. Central problem is the measurement problem. Several people have discussed this already, and that's basically if you think that the quantum state evolves linearly at all times, it leads to states of superpositions of macroscopically distinct alternatives. Sometimes people say that that is inconsistent with our experience, but if you say, I never see a piano in a superposition here and there, you first have to tell me, well, what would it be like to see a piano in a superposition of here and there? And I think the problem is that it doesn't even seem to make sense at first. And Bell put it nicely, if in fact macroscopic properties of things are always definite, then either the wave function as given by the Schrödinger equation is not everything or it's not right. And that gives us a nice way of classifying approaches. So you can take the first horn of Bell's dilemma, say the quantum state isn't everything, it's not a complete description of physical reality. And that includes, usually you think about hidden variables approaches with that, where you might supplement the quantum state by extra variables. But of course, any approach that says the quantum states don't represent anything in physical reality at all, also say that the quantum state is not, deny that the quantum state is a complete description of physical reality, as long as there is in fact something rather than nothing. Or you can modify the dynamics to suppress superpositions of macroscopically distinct states. So we've heard last two talks were talking about that. These, of course, aren't exclusive. And then you can say, well, reject both horns of Born's dilemma, Bell's dilemma, and say quantum states are in fact everything and they evolve unitarily. And that then you have to understand that. And hi, Simon. Some people would think that makes no sense, and other people say, no, that makes perfectly good sense. And I think if we look at what's happening, there's been a dialectic. Proposals get put between constructive and limitative approaches. And I'm thinking in particular of Bell's work. Bell criticized a lot of purported no-go theorems for hidden variable theories. And he was able to do that because he had the de Broglie-Bohm theory in the back of his mind. And he could look at all of these things and say, okay, we know that a hidden variable theory is indeed possible. And so he could look at the assumptions of these things and say, well, which of these assumptions is violated by the de Broglie-Bohm theory? And is it a physically reasonable assumption? And he decided from the existing no-go proofs that they were actually poorly motivated physically. But there is a sort of unsurprised. So if we ask the question, can there be a deterministic theory that does not require us to divide the world between observer and observed and does reproduce the probabilistic predictions of quantum mechanics? If the question is that possible? We know the answer to that. The answer is yes. Now that has a peculiar feature of action at a distance. And the question Bell asked himself, which he might not have thought of if he didn't have this theory in mind, is does a theory of that sort have to have action at a distance? And Bell's answer. I said that we've gotten a clearer idea of what the options are because people are putting forth options. And we also have a limitative results. I want to talk about certain kinds of limitative results having to do with compatibility with relativity, a topic that has come up already. I think it's important to distinguish two distinct sorts of questions that one might be asking when we say, is this theory compatible with relativity? One is it Lorentz invariant? Can it respect the symmetries of Minkowski spacetime? And the other question is, we usually think that special relativity says that there is no temporal order between space-like separated events. And if you think the cause and effect relations require temporal order, that means no cause and effect relations between space-like separated events. And that's a different sort of question. And one way to see that's a different sort of question is that if our background space-time is, say, a general relativistic space-time, then we don't really care whether our theory respects the symmetry of Minkowski space-time, except maybe locally and approximately. But this other set of questions is in full force, because in the general relativistic space-time, you still think that the causal structure of space-time is given by the light cone structure. Sometimes they're conflated. These two sorts of questions are conflated, but they're in fact logically independent. And just to illustrate that, you can have A without B. And this got mentioned in discussion. There is a version of Bohmian type theories for hypersurface Bohm-Dirac models, which basically the idea, you put in an extra field which evolves according to Lorentz covariant equations, which the structure of that field picks out a distinguished foliation, then you hang the dynamics of the Bohm particles on that. So it's got action at a distance, it's got, but the whole thing is indeed formulated in Lorentz covariant equations, and it respects the symmetries of the background spacetime. Think about hidden variable theories. For a while in the 1990s, there was talk about modal interpretations. Those were hidden variable theories of a sort. They supplemented the quantum state with some variables that had definite values. The idea is to have enough things with definite values that you get macroscopic objects, or at least determinate experimental outcomes. And we know that module, the usually sort of assumptions that go into interpret Bell-type experiments. If you have a theory like that, where you have some variable that determines the outcome of an experiment, then it has to have an action at a distance. Choice of experiment on one wing of the experiment can sometimes make a difference to the outcome of the other. Another question that you might ask is sorts of questions like this. They're going to have a probability distribution for the extra variables. We expect that to satisfy the Born rule. In relativistic space-time, you can say, well, okay, how do we link up space-like separated events? Can the Born rule be satisfied on arbitrary space-like hypersurfaces? There's a argument again by Dürr et al. That I think that any theory, whether it's Bohmian mechanics or not, that has definite trajectories for particles cannot satisfy this, cannot satisfy the Born rule postulate on arbitrary hypersurfaces. And there's a number of generalizations about that. And just sort of side comment, there's been a lot in recent years of discussions about Wigner's friend type scenarios, which typically involve multiple observers, and it's usually assumed that the observers have definite perceptions. And there's various theorems that show incompatibility with relativity there. I think that's the same kind of investigation, because if I'm saying observers have definite perceptions, I'm saying, okay, in addition to this quantum state, there are some variables that have definite values. And I don't know about you, I usually think that what I perceive has something to do with the state of my nervous system. And so a theory like that counts as a modal interpretation there. If I say my nervous system is always in a sufficiently definite state that my perceptions are definite. Some of that literature has actually reproduced some of the older theorems that have been were proved in the context of the modal interpretations. You can also argue from this that a theory like that does require a distinguished relation of distance simultaneity. What about collapse theories? When you first start thinking about collapse theories, and this was in fact Bell's reaction to GRW when he first heard it, okay, there's just no way they can possibly respect relativistic causality. And Bell said later, when you first heard of this in terms of Lorentz invariant, I thought I could blow it out of the water. Then what he did in that paper called Are There Quantum Jumps, is he took the GRW theory and it's formulated in terms of non-relativistic quantum mechanics, but non-relativistic quantum mechanics has what he called a residue of Lorentz invariant, which is relative time translation invariance. If you have two systems that are spatially separated and not interacting, then Schrödinger's equation doesn't really care how you link up events at this time and at this place and this place in terms of simultaneity. And he showed that the GRW theory had that feature of relative time, translation, and invariance. And he said, well, this takes away the ground of my fear that a theory of this sort cannot be fundamentally Lorentz invariant. Okay, so how do you do it then? And what happened then was there were people who made efforts to adapt the CSL theory to relativistic context. And they ran into problems, but not problems with respecting the causal structure of space-time. And the basic picture you have on a theory like that is it's a modification of the Tominaga-Schwinger picture, which is something that was in the late 40s and early 50s, often used as a formulation of quantum field theory, but sort of dropped out of the textbooks. What they use is something that I've called the stochastic Tominaga-Schwinger picture. The idea is for any, any Cauchy surface doesn't have to be a flat hyperplane. There's a quantum state associated with it. And the role of the quantum state on a hypersurface is it gives you probabilities for events to the future, which are conditional on events including the collapses to the past. And then you want to say, okay, if I'm going to go from one to another, how do I evolve it? So you might imagine here's one hypersurface sigma, and I've got another one which coincides with it everywhere except some region where sigma prime is to the future. I want to evolve it through this region. And in the Tominaga-Schwinger picture, there's going to be a unitary operator that's going to take you from that to that. If I want to make it stochastic, if I want to do a collapse theory, I say, okay, there's going to be some collection of operators, one of which is going to be the one that gives us the state on sigma prime. I'm going to operate on the state of sigma with one of these operators. Which one it is going to be a matter of chance, and write down a probability rule. Another way of saying that is you have operated valued random variables, call those the evolution operators. And if you want to respect the causal structure of relativistic space-time, if you evolve through a region here, evolve through a region there, at space-like separation, it shouldn't matter what order you do them in. And so evolution operators corresponding to space-like separations should commute with each other, and they should commute with observable operators representing observables at space-like separation. And this is something I think that people get confused about sometimes, because what is going to happen, if I take sigma prime and look at some subsystem over here, look at the reduced state of that, it might differ whether I take it from sigma or sigma prime. That looks like a contradiction to some people. But I think what you have to do is take very seriously quantum holism, as Professor Aspect mentioned, if I take a global state and look at a reduced state from a subsystem, that's not what Bell would call a local beable. That's not an intrinsic property of the thing. So sometimes people say the theory like this, what sort of stuff there is in a room can depend on what reference frame you're using, and that would make no sense. And so if you think about the ontology for such theories, usually people look at backwards light cone, mass density at a given place. And I think all of this is consistent with quantum reality as Roger was talking about it. So what problems did they have? Well, this was something that Bell was interested in the last few years of his life. When people tried to adapt CSL to relativistic theories, what they had was divergence of energy production from the vacuum. So Philip Pearl in a survey said, good news is collapse works well. Bad news is collapse works too well. And there's an argument that that's unavoidable. This is from Pearl. Basically, the idea is that if you've got a certain probability for a certain excitation from the vacuum, you have to have, if you have Lorentz invariance, you have to have the same probability for every boost of that excitation, and there's just no way to keep that finite. Now, we actually do have relativistic collapse theories, have been formulated by Daniel Bedingham and Philip Pearl. There's something weird about them. They introduce a pointer field which commutes with itself not just a space-like separation, but for any 2 points, even time-like. It has no intrinsic dynamics. Okay, that's not normal. Right? So call those non-standard fields. And okay, let's ask a similar question. So we had a we had a hidden variable theory, had this weird, unexpected feature of non-locality in it. Bell says, is this inevitable for a theory point of this type? You might ask if is this inevitable for a theory of that type? And that's a question that I was trying to figure out a couple years ago, and I convinced myself that the answer was yes. That if the vacuum is stable, and it has to be completely stable because you can't have just a little bit of excitation in the vacuum, then what happens is that you get unitary only evolution, meaning no collapses for all standard states, which are standard states are states you get by operating the vacuum with standard fields. So you need non-standard states. You need non-standard fields in order to get any collapses going. But the question is, well, should a collapse theory function in the vacuum? I think the idea, and I think this is what I was thinking a number of years ago, is that, okay, like, we don't really care what happens in a vacuum. We're really interested in what happens in the presence of matter, and we like GR, so we think that in the presence of matter, we don't have Minkowski spacetime, we have curved spacetime. But I think the idea was that should be negligible. We should be able to do this. Our theory should work in situations in which the curvature of space-time is low enough that we might as well be in Minkowski space-time. But maybe that's wrong. And something I've been recently thinking about is that, okay, maybe this kind of result, maybe this sort of problems that people ran into when trying to do a relativistic version of CSL is a hint from another direction that collapse actually shouldn't work in Minkowski space-time. The collapse requires curvature, and it might be a hint to something like these proposals by Dioschi and Penrose that they came from a very different perspective, are on the right track. I think that when you get similar conclusions from different kinds of perspectives, that's sort of a clue that you maybe are on the right track.